you take a 10% penalty. From 24 hours and 1 second late to 48 hours late, you take a 20% penalty, and so on till it gets to 50%. If you submit later than 50%, we're not going to grade it. You just get a 0. Okay. So there is a certain potential strategic advantage to submitting late if you feel that extra 24 hours can bump your score enough that it makes up for the 10% loss. I will leave all that game theory to you to figure out. But there will be no, so don't, I'm saying this now because the first assignment, you want to set the policy early on. There will be no extensions. Okay? All right. The next most important thing, interactions. So unlike what you may have heard about mathematical sort of things, this algorithm is a social activity. So it's more fun to sort of argue with your friend. It helps to think. So I don't mind if people talk to each other. However, you must cite every person you speak with. So you must have a little list in the beginning or in the end saying these are the people I work with. And yes, I do cross-check these things. So no, if X says you work with Y and Y says you're alone, someone's got a problem. Either X was working with Y and Y didn't know it, which is a problem. Or they were working together and Y chose not to cite it, which is also a problem. So please make sure you do it. And B, when you have to decide, did I collaborate with someone? Be liberal. Did you talk to them about the problem? Yeah, yes you did. Okay? So if you do this, there will be no problems. If you don't, then we'll start having unpleasant conversations about who is cheating, who is not, and none of us wants that. You don't want it, I don't want it, none of us want that. Okay? Lastly, on referring to other material. Anything I say in class, you can use without any referencing. You can use it as if it were in your brain, because it should be. Anything I provide from the notes, you can use directly without referencing. If you use anything else that is not something I said and is not in the readings, you must cite it. If you go to Wikipedia and find something, you must cite it. If you go to Wikipedia and find the answer, fine, you win, I lose. You must cite it. Also great. It's my fault if I gave you a question where you could find the answer so easily. But you must cite it. If you do not, that is then a problem. And then we have to have another unpleasant conversation. Okay? The basic rule of thumb is, the way you go from cheating to scholarly referencing is by adding quotation marks and adding a citation. It really is as simple as that. Acknowledge where you get your information, there will be no problems. Yes?
Do you have a preferred format for those citations?
I do, but I'm not going to impose it on you. That would require more LaTeX mojo than you'd be willing to learn. Okay. If you're curious about it, I can tell you how I do it. But somewhere in your homework, you should say something. If you want to have a section at the end saying, here are the things I use, if you want to insert it in, I don't care. As long as the information is there, I'm happy. Right? When in doubt, ask. If you come up with an assignment and I say, where is the citation? So, oh, I didn't think I needed to. No. You're not 3 years old. If you have a doubt, ask. If you have a question, ask. If you ask me 5 minutes for the deadline, I may not answer. I might be sleeping, or I might not. So again, plan ahead. You can do this. It's not that hard. Just plan. Okay? I'm being extra stern here just because, it's the first assignment. I want to make sure everything's clear up front. I don't want to have to be repeating this for assignment 6, because it's boring. The rest of it should be there. Read the homework policy, look at the assignment, get the PDF, get the LaTeX. Do your magic on it. It's, I would like, you can ask me how hard I think the assignment is, and then my answer will be completely useless to you, because it doesn't mean anything. So, and it really doesn't matter. There are 5 questions. It's 60 points. So there's an initial question on recurrences, and there's a bunch of recursion / dividing conflict. This is a clue, if you're wondering how you should go about attacking the problem, well, this is the first assignment, so it's probably going to be about recursion and dividing conquer and things like that. And so, like I said, the best way to do these kinds of assignments is today or tomorrow, go read it. Mark off the ones you think are easy to do. Maybe you just start scribbling on a piece of paper and just doing them, whatever you can. And then just spend maybe 15, 20 minutes on a problem just thinking about it if you have that time. Just think about where you might start. And then put it away. And then come back to the next day and then think about it some more. This will actually give you more chance of actually getting an answer than if you just say, okay, I'm going to spend this one day and cram it. It doesn't work that way, not for these kinds of problems. Okay? Yes?
But if you talk to somebody in discussion forum, then everybody can see it. You don't have to tell who.
If you post a question on discussion forum, then yes, this is a public, at least in the class context, so you don't have to mention, yes, I posted, because I know you did, so you're right. If you post a discussion forum in the Canvas, you're fine. Now, if you go to Stack Exchange and post something there, and which everyone does, but basically, I lurk on some of the Stack Exchange forums, and basically every December and every April, suddenly all these new users are showing up with all these questions. And you poke a bit more, oh, it's a final exam question, now go away, don't bother. Yeah, that kind of thing you better cite. Okay. Now, again, I won't catch all of you. Some of you might be getting away with it, but the question is, do you want to take that risk? So don't. And the other reason to, even if you're going to talk to other people, to try, so the best kinds of collaborative discussions happen when you've done your own thinking first. Because what happens is people have very different ways of thinking about problems, and they interact, good things happen. If you go to a discussion cold, then all you're doing is listening to what other people are saying. You might even be able to get the answer. You might just listen to what they're saying and figure out how to write the answer yourself. But you won't have learned anything. And this won't hurt you now, but it'll hurt you in the final exam. Because the final exam, you're in the room, there's no option for discussion. Then you are on your own. So all these homeworks are basically your practice drills for the final exam and truly for learning the material itself. So even if you're going to go and sit in a group and talk to people, it really will benefit you to think about the problem yourself first. Bring your own knowledge to the gathering. Even if it's a wrong direction, at least you've thought about it. Those things help you immensely. I cannot emphasize how much it helps to actually do things yourself. Okay. All right. Yes?
If two people, A and B, they talked that, but ended up A is helping B a lot. So
Yeah.
B still should cite A.
Everyone should cite everyone, yes.
Okay.
Words were exchanged.
And including TAs?
Sorry?
Including TAs?
No, you don't have to cite the T's. It's a job to help.
Okay.
Now, if the TAs give you the answer, I will have to have words with them. But I've given them strict instructions to be as cryptic as possible. And I also told them that they can blame me. That if you complain to them, then you should all blame me for that. Because that's my thing. You know, when you come and ask for help, so this is what typically happens, right? Someone comes to me and says, oh, I'm getting stuck on this question. I say, okay, to tell me. He says, well, here's my answer. I'm like, okay. Do you think that's the right answer? My usual response is, I don't know, what do you think? And then this goes on for a bit longer and they get annoyed and they stop asking. Our job is to guide you, to help you, to maybe say, you know, have you thought about this? Have you thought about that? Are you sure about this? When our goal is not to play a game with you where if you ask the right questions, you unlock the secret code and you get the answer from this. That game is not the game we're playing. So our goal is to enlighten you, to befuddle you, to confuse you, because in that moment of confusion actually comes deep insight. Telling you the answer is not helping you at all. You want to be confused. You want to feel frustrated. That's where the true knowledge will come from. That's where learning is not meant to be comfortable. It's meant to be painful. Because that's when you actually learn something. So keep that in mind. If you're feeling confused, you're feeling frustrated, you actually might be on the right track. Because you're actually fighting with that problem. Okay? Have you heard this? How many of you heard this quote by Erdos, the famous mathematician? So he's talking about research problems, of course, but his quote is, problems worthy of attack prove their worth by fighting back. In other words, a problem that's good enough to try and solve will not let you solve it easily. That hopefully is not the case with these assignment questions. They will probably put up a little bit of resistance, not too much. But they should put up some resistance. Don't expect it to all just work. Okay. Again, maybe I'm saying things you already know and that's good. So, but I just want to just emphasize the point if you're feeling a bit of math shock after some time away from the stuff. Okay. So that's so much for the assignment. Any last questions before I move on? Okay, good. So let's continue where we left off last time. Just to recall, we were starting to talk about dynamic programming, which is, we're calling a smart recursion. And we looked at one particular problem, the problem of the longest increasing subsequence. You're given numbers x1 through xn, find a subsequence xi1, xi2, xik such that xi1 is less than xi2 less than xi3 all the way up to xik, and k is maximum. Right? So that's the longest part. This is the S, I, L. Right? Longest increasing subsequence. Yes? Okay. And we looked at, so what we said was that the trick with dynamic programming as a sort of a recursion on steroids is that you think recursively, you formulate the problem recursively, but then you look at it and you kind of unwrap it. In this particular case, we had looked at one particular recursive formulation. We said, oh, the way to think about this is to say, okay, let's formulate a subproblem let's say we define the subproblem LIS I comma j is equal to the length of longest sequence, so longest answer recursively, starting at j, right, where all elements are more than xi. Right? So this was the recursive formulation we had decided to work with, in the hope that this would give us a way to form. So we don't really know if this formulation is going to help us. It's just some way of defining a subproblem, and the hope is that we can express our true problem in terms of these subproblems. So of course the first thing we had to check was that, is there any way to express the true problem as in this form at all? And yes, the actual problem LIS is equal to LIS 0, 1, right? You want the length of the longest subsequence starting at 1, where all elements are more than x0. Wait, what's x0? Set x0 equal to minus infinity. This is called a sentinel value. It's like adding an extra element to an array which is as small as possible. Less than the minimum of the items. Right? And so yeah, so at the first thing to check is yes. If we could somehow solve LIS 0, 1, then we've actually solved a problem. So that's good. One of the entries in this IJ sort of matrix that we're building up is going to solve it. But the real question is, okay, can we express this in terms of simpler versions of the problem? Right? Where simpler could mean, well, we'll see. And so what we said was that, oh, we can write LIS I comma j is equal to one of three things. It's either 0 if j is more than n. Right? If you've fallen off the edge, there's no sequence. The answer is 0. There's no sequence. If AI, oh sorry, not AI.
Greater than?
Someone saying something?
Do you mean j is greater than n?
I do. Thank you. Very good. If xi is more than xj, well, what does that mean? If xi is more than xj, then the length of the longest sequence starting at j is really the length of the longest sequence starting at j plus 1. Because j can't be in that sequence, right? So this would be just LIS I comma j plus 1. And if not, then you have two possibilities. Either you pick j to be in your sequence, right? So there are two possibilities. Either you pick j in your answer, then your LIS is 1 plus LIS j comma j plus 1. Because now you want the longest sequence starting at j plus 1, where every element is more than j because you picked it. Or, if not, it's just what we said before. So, and then take the max of these two, right? So what we've done is we've expressed the problem LIS I comma j, hopefully recursively, in terms of other subproblems. Now when I say hopefully recursively, the whole point of recursion is that at some point this has to terminate, right? So when you look at this, you say, oh look, when I express LIS ij in terms of LIS ij plus 1 and jj plus 1, notice that I is less than j to begin with. So all that's happening is that these numbers are increasing. Eventually they'll go all the way to the end and we have a base case there when j is more than n. And we have a base case when I is equal to n, of course. So this is in fact doing a recursion in the right way where there's actually a base case at the end. And schematically, if you looked at your matrix of values you're filling in for I comma j, and I is indexing down this way and j is indexing across this way, we're saying then that the entry you want to fill in, this one, is influenced by the element in the next column, right? This is LIS ij plus 1, but it's also influenced by an element somewhere further down in the next column. Right? These are the two elements that can affect the value you see there. And then correspondingly, these two elements are affected by the next one, and so on and so on. And we know that in the base case, these numbers are going to be 0 on the edge here. They're all going to be 0. So, step 1, formulate the problem in terms of subproblems. Step 2, write the recursion. Step 3, verify the recursion, that it's actually correct, that we just talked about here. And step 4, unroll the recursion. That's the step that makes this dynamic programming. Where you do the smart recursion, you think top down, but then you implement it bottom up. Where you say, look, I have two parameters that are describing my subproblems. Each of those values range between 1 and n. So I have this n cross n set of possible subproblems. And if I look at how it's being updated in this sort of convenient matrix form. And if I look at the flow of information, I can see that the information I want, the destination, is here. This is what I want. Right? And to get there, I have to fill in all these other values from here. And I know what the base cases are here. So I can actually fill this in essentially backwards. And that recursion will tell you how to write the code for this. Because now instead of doing a recursive call, you now say, okay, I can actually store these values. That's the memoization part of dynamic programming. And you can do this. And to see how long it takes, well, it needs n squared space, clearly. So yeah, you have to fill these entries. To fill in each entry takes how much time? Constant time. Just look at two other entries. So you have n squared entries. It takes constant time to fill in one entry. It takes n squared time. Right? And so this solution for LIS takes n squared time, and I'm ignoring the O's, and n squared space. This is typically what you will see with dynamic programs. If it's a simple one along a sort of an interval, you might see linear, but you'll often see things like n squared time, because you just have to fill in that many entries. You will also often see n squared space, which is not great at all. I mean, n squared space is a lot. But if you look at these things now carefully, I think these are sort of super optimizations you can do. You can say, oh wait, do I actually need to store this entire matrix? It turns out for this entry I need these two. For these I need those. But once I've computed this entire column of information here, that's all I need to get the next column of information. And then this is all I need to get the next one. So even though you're actually building up entries in the entire matrix, you don't actually have to store them all at the same time. You can sort of do a little wave. You first compute this column, then overwrite it with this column, then overwrite. So you may need to keep two columns, the new one and the old one. But that's all. So you keep one column for the old values, one column for the new values, and you just ping pong them. And so your old becomes new becomes old. Again, the pseudocode is in the notes. I'm not going to write it here. But it should be clear to you that this will reduce our space from n squared to n, right? You just have one column. So clever observation, once you've done the recursion, once you've verified the recursion, once you've written out the unrolling, once you've done the memoization and figured all this out, then you can go look and say, oh, wait a second, maybe I can optimize something else. And this will go down to next week. Okay? So we didn't talk about this last bit, but this is basically, a quick sort of overview of what we talked about last time. And it's important to realize that in all of these things, there is no one way to solve these problems. There is no single dynamic program, the right one you need to get, and you think and think and think and think till you get it. Anything that allows you to do this will work. And in fact, for this problem, there is a different dynamic program that works equally well. So the way this dynamic program was set up is by formulating a certain kind of recursive problem. LIS I comma j means find the subsequence starting at j where all elements are more than I. Right? But that's not the only way you could do this. You could say find the longest subsequence of starting at j, which actually has j as its first element. You don't need that extra parameter. So in particular, let's come up with a new formulation. And this is only one parameter in it. I'll just call it I for now. So this is the difference, right? Instead of saying there was some I in the past and there's some J here, you just have this one thing. And once again, you could say, okay, I now have this different formulation of the recursion. I don't know if the recursion works anymore. Okay. Some of you may have seen the notes, you may know the answer, but if not, it's a good exercise. Take 3 minutes. How would you express this? First of all, verify that this will actually give you a solution to the problem you care about. And then express this recursively. Go. 3 minutes. Again, if you've seen the notes before, you probably know the answer. But even then, just close your eyes, forget the notes, and try to reconstruct it. It's also a good exercise. So is the goal clear? Again, first check that this formulation of the problem actually gives you a solution that you want. I mean, some value of this I will give you what you want. And then secondly, formulate it recursively. Okay. Tell me. So I don't necessarily want to know the answer right now. I will in a second. If you were struggling to conceptualize what you need to do, that's what I want to hear. But anyone feel that they were, were getting a little stuck or not quite sure how to proceed, or any thoughts there? No? Okay, good. So then, would someone like to venture a guess for an answer? Anyone?
So I think it'd be, so you take like the maximum value of
No, I don't want words.
Uh,
My brain does not comprehend words. I want things to write. In other words, LIS prime I equal to...
LIS prime of I max of LIS prime of J, where J is greater than I, and J is less than or equal to N, and X of J is bigger than X of I.
There's only one way to know if this works. We try. Someone give me a sequence. Numbers, please. Anyone? Someone. Tell me a number. Not 4.
2,
9.
7, 12,
20? Someone say 20?
20.
Yeah, that's enough. You all are very nice. I did this once in a previous class, like 3.2, 7.65, and then they all got carried away. Someone said pi, and someone said pi squared, and at that point I shut it up. You're all very good. Keep that attitude. Don't, you know. Okay, let's run it. So, okay, so first of all, what is the answer to my problem? It's LIS prime of? Huh? LIS prime of 1, right? Is it LIS prime of 1? What's the answer to my problem? Are you sure it's LIS prime of 1? Yes?
You have to define, just like before, defining to move the sequences.
Why can't I just take LIS prime of 1?
This one was start 4 is
So if you start, it's basically saying I'm forcing you to start with the first one. I don't know if that's the right answer. So imagine that there's some kind of, which is a 0th element. So I want LIS prime of 0, yes? But that'll have one extra element in it. So I really want LIS prime of 0 minus 1. Because I removed that first element. Okay, fine. So we've checked that now. And this is what the answer we want, right? This is the LIS, okay? So now let's run. Okay, so now if you look at this expression, what it's saying is it's trying to do this thing backwards, right? So LIS prime of 0 is max LIS prime of j for all j more than I, right? So it's a max of the one starting here, here, right? Okay. Well, let's go here. What's the LIS prime of this value? So we'll write them down below here in red. What's LIS prime of, let's see, so this is elements 1, 2, 3, 4, 5, 6, 7. And what's the LIS prime of 7? No, LIS prime of 7 is the max of LIS prime of j for j more than I, j less than or equal to n. LIS prime of 7 is 0, according to the definition. LIS prime of 6 is the max of LIS prime j, j more than I, j less than n. Well, the only one there is 7, that's 0. Okay, so this is 0. Is this correct so far?
No,
What's the problem?
you have 1.
Sorry?
Gotta have 1.
Gotta have 1.
Add.
I gotta have 2 sometimes. If you wanna have 1, where's the 1 gonna be?
I'd say it's 1 plus the max.
You would say?
I say.
You say? Okay. Be confident. If you're gonna be wrong, be confident to be wrong. It seems to work for some people. Okay, now let's try it. What's LIS prime of 7? Well, it's 1 plus LIS prime of nothing. Okay, good. So we got a 1 there. What's LIS prime of 6? Well, it's 1 plus max of the 1 for 7. So that's 2, because 12 is less than 20. What's LIS prime of 5? Well, it's the max of, it's 1 plus LIS thing for all of this. So 7, 12, and 20 are bigger, so I can pick any of them, and this is a 2, so this would be a 3. So far so good. It appears to be working. So this is a good lesson here. When you do something like this, check it. Don't just write it down and assume it's true. You'll be surprised how many homework assignments I get, or someone just wrote something and said, well, I wrote it, it must be true. It's in code. It must be true. Check it, and then you'll see if it works. So now we have a conjecture for what this recursion might be. And now we have to prove that this is correct. How do we prove that this works? Any kind of recursion like this, what is the way to prove that it's correct?
Induction.
You were saying something?
Induction.
Induction. So the proof by induction basically goes like, assume LIS prime k correctly gets the length of the longest increasing subsequence of xk through xn starting at k for all k less than I. Now look at LIS prime of I. If you look at LIS prime of I, okay, either it takes, so it takes I and has to look at whatever comes afterwards, right? If you look at the sequence coming afterwards, that gives you the correct length. You've checked that xj is more than xi, so you actually can glue on I onto it. So therefore, by the induction hypothesis, this is correct. And you can verify the base case as well. Yes?
It needs to be 1 plus max and not max of 1 plus, because for 9, it doesn't work.
Ah, very good. So it's not working. So tell me where it goes wrong.
So at 9 again, when
Yeah.
you check for max of 1 plus LIS of j,
Yeah?
it doesn't work.
Why not?
Because there is nothing that's.
Okay, so let's look. What is the only elements that qualify are this and this.
Yeah.
So, and now this 2 is bigger, so this will be 3. Is that not correct? Max of 1 plus something is 1 plus max of something. Is it not true? Am I missing something? He looks confused. I feel I might be wrong now. No?
Oh, okay. Sorry.
That's all I'm saying. Okay. But you're right. I mean, it's cleaner to think of it that way. From the induction point of view, it's cleaner to say, look at the best sequence that comes later, then add on to it. So semantically, it makes more sense to say 1 plus max that. And I was being sloppy there. But it's not wrong. I kind of lucked out. It's not wrong to write it this way. It might, other than okay? All right, good. So once you've written this out, this recursion, right? So we've got step, I don't know. We've got step 1, and then we verify it, which is step 2. Now we can unroll it and say, oh look, we actually have a single table we need to maintain, right? And to fill out the value for I, what do we need to do? We need to look at all the values bigger than I, and that influences the value for I. So you can now clearly tell how long this will take. How long will this take to solve this problem? It takes I time to process it takes n minus I time to process the ith entry. So the overall time will be n squared, right? Space required is linear, which we got in the previous case too, but after some work. Here the recursion just gave us the linear space directly. But what's interesting is the following. Look at the difference between this dynamic program and the previous one. In this case, how long is your update step take? The update step takes linear time in the worst case, right? It's taking a long time to update an entry. In the previous case, you had a bigger matrix, but it took constant time to update each entry. So they're different. They have a different kind of flavor to them. In some sense, we're not saving anything here. We managed to compress the space, but at the cost of spending more time per update. You just have a different dynamic program. And that's why I wanted to show this to you, that there are different ways of building a dynamic program that might not have different ultimate costs in terms of time and space, but just have a different structure to the way they work. And so when you're looking for dynamic programs to solve your problems, there is not necessarily one single answer you're hunting for. You could have different answers. As long as you can do these steps and verify them, it'll work fine. Okay? All right. Any questions? Actually, before I move on. Any questions? Okay. Next problem. Now again, I'm going to have you do a bit of the thinking yourself. We're going to start from scratch. This is a problem you've probably seen before again. It's in the notes, so if you've seen it before, that's fine. So given 2 words, so you have W and W prime. find a shortest sequence of insert, delete, replace, insert space, delete space, oh, sorry. Um, well, let's see how I want to say this. Hold on. There are different ways you can formulate the question. Okay, yeah, insert letter, delete letter, replace letter, to change W to W prime. So for example, one example that's in the note says I want to go from food to money, right? So I change food to that's a replace operation, right? Let's see, what should I do next? I'm going to replace mood by right? I'm running out of space here. Then I'm going to do N, E, right? And then finally, right? So I have how many steps? I have 1, 2, 3, 4. Now I don't know if this is the best one, but this is a sequence. By inserting, deleting, and replacing. Right, so this is I didn't delete anything here, but if you go backwards, you have to delete something. Wait, yeah, I inserted that. All right. So the problem now is to find the shortest sequence of operations that does this for you. And then the question is, how might you go about doing this? And so, again, the goal is to, first of all, try to think of a recursive formulation of the problem without worrying about efficiencies and other things. Think of a way of expressing this idea recursively. And in order to do that, you have to think of a kind of a subproblem definition. Because recursion means you have some problem, you express it in terms of subproblems. And eventually you solve the one you want. So first step is to think about how you might break this into subproblems. And the second step is to use those subproblems to express this recursively. Once you have that and you verify that it's correct, you can now start trying to unroll it and seeing what it means actually for your problem. So why don't you take 4 minutes to think about how you might go about it. For those of you who don't know, this is the Jeopardy sort of quiz show. Okay, I'll give more time than that. It's like 30 seconds. There's actually entire loops. You get the whole hour loop of this music. I don't know how annoying that would be. But it seems like pretty annoying. Nope. That's annoying. Okay. Thoughts? Your first goal is to think about how you might express this recursively. Any thoughts? Yeah?
We'll compare the letters, match the character.
Dividing.
That's not recursive.
Dividing it.
We'll match the characters and then recursively call with the substrings of the W and W.
So maybe I'm not understanding. So I have two strings. Let's say there's A1 up to AM. This is one string. And this is B1 up to BN. This is another string. Okay. So tell me.
We'll compare A1 and B1.
We'll compare these two. Okay. And?
If they match,
Yeah.
then our recursive function will be from A2 to AM
Yeah.
and B2 to BM.
And if they don't?
If they don't, then so we'll see if you have to insert, replace or delete.
How do you know?
We'll try all the three and we'll find the minimum of.
So what does all the three mean? Suppose they don't match. So A is not equal to B. Right? So this is the case of okay. So F and M don't match. Now what do you do?
So what we do is we'll since they don't match, now we need to edit it by one.
Okay.
Either it could be using the replace or insert or delete.
So what do I do?
So you should take minimum of these three operations.
Which ones?
Minimum of 1 plus, and then you replace it with them. So minimum of the string OD and ONUL. That corresponds to replace.
Okay.
So again 1 plus DO. So if you are doing an insert, then it would be again OOD
Okay.
and money.
Okay.
And the last one would be 1 plus.
I assume it will be this. Yes? Is that right? Food and honey? Yeah? Okay. So now you have a recursive, so what is your recursive subproblem now? Your recursive subproblem appears to be characterized by where you start the subsequence pointer on the first one, and where you start the subsequence pointer on the second one, right? So we can think of this as a parameter j and a parameter I, right? So what is the, if you think of the problem, if you think of this formulation as right, then what are we saying? We're saying this is basically equal to the max of 1 plus ed I plus 1 j plus 1.
Isn't it minimum?
Oh, min. Sorry. Okay,
We also need a base case.
what's the base case then? Where will the base case be? The base case will be at the end. Okay, so what is the base case then? So you want base cases of the form n comma m, which what will this be?
So the string to which we want to convert is of length 0.
No, n and n. I'm looking at the last element. I just have a string consisting of one character in one and one character in the other. So this will be basically be 1 if a n, sorry, mn. am is not equal to an and is 0 otherwise, right? If the last two letters match, you don't pay anything, otherwise you pay something. And you also need a base case for what else? You need a base case for all, you know, ed I comma n and ed n comma j. So the row and column, the bottom row and the bottom column, right? And this will be basically ed n comma j basically means you've taken everything up to the end. Well, let's just call it n plus 1, make it simpler, right? This will be an empty string and you have to delete all those j things there. So that's cost n minus j, right? And this will be again n minus I. Okay, so you've got the base case all set up. The first question is, how do you prove this is correct? And the way you prove this is correct is by induction. You say, okay, is it true in fact that I can express this in terms of that? And one way to argue this is that suppose it's not the case that this can be expressed as that somehow this is less, right? It can't be more, but it could be less. That the answer you get for this, the optimal solution for the edit distance for strings starting from I through m and j through n is actually better than what you could get from this operation, right? Well, if that's the case, what's going to happen? If it's in fact the case that this gives you a better solution than any of these things, well then look at the first two characters, and if they're you know, look at the match you get. You've either chosen to do an insertion, deletion, or replacement of the first two characters, and you have the rest. But we already said inductively that for the rest of it, this is the correct formulation to use. So then take that formulation, add this, and now you have a contradiction. Because now that was better than that, and that's smaller. So in other words, the way you prove things by induction either is by showing that if it's true for n minus 1, it's true for n, or you can prove by showing if it's not true for n, then it's not true for n minus 1. It's a contrapositive. So the way to think about this is that if in fact this is better than what you get from the recursion, right? The answer you get here is better than what you get from computing the recursion directly, then you can get a smaller case where in fact it's better than what you get from the recursion. And in fact then you get a better case where, again a smaller case where it's better than what you get from recursion, down to the base case where you're saying your answer is better than this, which is clearly not possible. So induction proofs work in two directions. You either work forward positively, or you work backwards saying, aha, I got you in a contradiction. Right? In this particular case, it's kind of easy to see that the reverse way works better. And in fact, that's how it's proved in the notes. But you can think about trying to prove it more directly. Any questions so far? Yeah.
I think there's one problem with it, because if the characters are the same,
Yeah.
you don't need to add one.
So I may have been a little sloppy in how I said it. I don't think he intended it that way. I think his point was look at the characters. If they're the same, so there's a fourth case that I was being careless in order of writing. It's basically ed of I plus 1, j plus 1 if ai is equal to bj. I think that was one case it would consider. So now you take the min of all these four cases. But that's correct. Yeah. Other questions? So again, we thought recursively, we came up with a formulation, a sense of a substructure, a state if you wish, a way of describing a substate, and then we express this recursively. We use induction to prove it's correct. And once you do this, you can now see that your state space for this problem has got two parameters to it, so it's going to look like some kind of matrix. And if you visualize the matrix now, it's going to have some matrix here with I and j on both sides. The two strings, essentially string 1 on this side, string 2 on this side. And if you look at the ijth entry, right, it's going to be affected by the entries right next to it. So this entry that we want to fill in is going to depend on this entry, and this entry. And they're all going to influence it. So you can see the flow of information is going to be from one end back to that. You could implement this the other way around. In fact, in the notes, they implemented the other way around. It doesn't really matter. The strings you can read them reverse ways. Okay. And now you can say, okay, is there some clever way I could save memory here? In fact, you can do the same trick here, because again, to solve one column, you only need the previous column. You don't need to have everything else. You could again do this ping-ponging trick and save some space in the process. Right? And each update is only constant time. So the total amount of time is going to be n squared, because there are n squared entries. Each update takes constant time. The amount of space naively is n squared, but with a bit of work, you can get down to n. And that's your address. And to this day, by the way, we don't know whether we can do better than that. And in fact, there's some evidence now, as of a year ago, suggesting that you can't do any better than n squared for that distance. So it's a separate thing. It's not to do with programming, but the question of can you do better than quadratic for doing n distance, and you have to go through this whole table. There's something smarter you can do. There is some new evidence saying that this is seemingly unlikely. Now, what seemingly unlikely actually means is a question of complexity that I'm happy to tell you about offline. But it just came out just now, like a year ago. So this is a sort of an area of active interest. Okay. So let's try to sort of distill out what we're seeing from all of this, right? So when you think of dynamic programming as a recipe, so when you talked about divide and conquer, our recipe was find a way to split it, and then balance check how long it's going to take to put the solutions back together, and how many sub-pieces we get, use the master theorem to guide what kind of efficiency we want. In the case of dynamic programming, the steps are a bit more involved. Yes, you did think recursively, but you weren't splitting per se. In fact, you have all these overlapping subproblems, so you're not splitting at all. So the first step is to formulate a recursion. In this sense, it's very much like the previous case. Think recursively. Formulate a recursion, right? Verify that it solves a problem, that original problem can be expressed in it. In other words, that there is a way that one of the subproblems is the thing you're looking for. This doesn't mean it's correct, it just means you can express the original problem. Prove correctness, usually by induction. And at this point, you've established that your algorithm is correct. What you do now is make it efficient. So now you do the unrolling. Unroll, memoize subproblems. And if all goes well, you actually have code. You can actually write down the algorithm. But all of these things need to happen before you can be convinced that you have a dynamic program that works. And most commonly what will happen is you actually won't have a correct recursion. That's the easiest way to slip up in a dynamic program. Once you get to this point, you may not be completely optimal in terms of how you improve, but you'll probably get something reasonable. But usually a dynamic program, the error you make when you try to solve a problem is in assuming you have a correct formulation of the recursive structure when you actually do it. Okay? And we will see next lecture how you can trip up when you start thinking greedily instead of in a dynamic programming sense. Right? It's very easy, it's very tempting to say that the recursion is going to work by choosing the best thing I can do right now and then recurse. That's actually a greedy algorithm, choosing the best thing you can do right now and recurse. Dynamic programming kind of works backward. It says, well, look at the best solution. How must it have looked at this first step? Choose of all possibilities. So imagine that you solve that problem, and now you know what your first step needs to be. So your first step is the last thing you decide in some sense. Whereas a greedy algorithm, the first step is the first thing you decide. We'll say more about this on Thursday when we compare this to greedy algorithms. But something to keep in mind, that's where things often go wrong. So even though it might seem like you have the first 3 steps nailed, be suspicious and try it. And again, I'm emphasizing this recipe not because it will work every single time, but it helps organize your thinking. And some problems will get more complicated. Sometimes you have your dynamic program consists of instead of n squared or n cubed, it consists of n to the d states, or even n to the log n states. It gets very complicated. It's no longer even polynomial time at that point. But the basic principle is the same. Okay. Questions? So we've seen dynamic programming with sequences. We've seen that you typically get a state space that looks like a bunch of things in an array, or it looks like a bunch of things in a matrix, and you're filling stuff out. But it doesn't always work that way. Sometimes you're doing dynamic programming on structures that are not lines and are not matrices. In fact, you're doing dynamic programming on graphs, or on very special kind of graphs. In particular, we're going to look at a way to solve hard problems. We haven't really talked about what hard problems are in this class. If you've taken algorithms class before, you may have heard of NP hardness, but we haven't really talked about it here. We're going to talk about how you can solve hard problems on simple structures using dynamic programming. In particular, we're going to look at trees. So again, a refresher, a graph, at least in algorithms class, consists of vertices and edges between them. So E is some subset of V cross V. And you have vertices, draw lines between them. Well, it doesn't have to be lines, I'm just drawing an abstract graph. This is a graph. These are vertices and there are edges between them. Graph, of course, is a very rich object. It captures all kinds of data where you have relationships between things. It's one of the most powerful tools we have in computer science to think about data along with points. And a tree is an undirected acyclic graph, and so it has no cycles, certain cycles. Right? I can't add this edge because that would create a cycle, so it's not there. Oops. So a tree is, generally speaking, undirected and acyclic. Every tree on n nodes, n vertices, n nodes, must have n minus 1 edges. This is an amusing little fact. If you didn't know, you can try to prove it. All trees have to have n minus 1. If you add one more edge, you're going to cycle somewhere. Okay. Now, a lot of interesting combinatorial problems you can ask on graphs. Many of them are very hard to solve. They're hard in a kind of formal sense. But a lot of them get easier when your graph is a tree. Intuitively, a tree doesn't have all this kind of connectivity structure in it. So you can kind of separate things out. Recursion works. It's not divide and conquer per se, but some kind of recursion works. And so what I want to show you is one example of a problem where you can apply dynamic programming to solve a tree. And this paradigm is a very common paradigm you can apply to all kinds of questions. So what is the problem we're going to look at? The problem we're going to look at is the problem of independent set. An independent set in a graph is a set of vertices that have no edges between them. So in the graph above here, if I want to mark out independent set, I could mark this vertex, I could mark this vertex, I could mark this vertex, and I can't mark anything else now, because every other vertex is adjacent to one of these things. So this set is an independent set. Right? Now if you want to find an independent set in a graph, it's pretty easy, right? Just take one vertex. That's always an independent set. What makes the problem interesting is when you want to find the biggest independent set you can find. Intuitively, the more things you put in your independent set, the harder it gets to add more, because now all these vertices you've added have connections to other things. And so there's a whole bunch of things you can no longer add. Right? So the hard problem here clearly is to find how big your independent set can be. I've given one of size 3. There are 3 vertices in it. I don't know if this is the best one. Maybe I can do better. So the max independent set problem is given a graph G, find an independent set of largest size. Now this is a depressingly hard problem to solve. There's an obvious algorithm which is very expensive that says take every possible subset, check if there are any edges between them. If there is, reject it, otherwise keep it and take the biggest one you get. It'll take time exponential in n. It'll be n times 2 to the n, or n times 2 to the n. Not a great algorithm, but it'll do something. But in general, we don't know if you can do any better than that. We don't know if you can get a problem in time algorithm. I'm not sure you can do it. So this is a very hard problem. But it turns out if your graph has a nice structure to it, then you might be able to do that. And in particular, if your graph is a tree, then you can do that. And if your graph is a tree, then we're going to try and use dynamic programming to solve it. So find MIS, so that's max independent set, also known as MIS, on a tree. So let's draw a tree. How might you go about finding, and how might you go about formulating a recursive expression of the independent set in the tree? So I want to say something like, to solve the problem of independent set on a tree, I want to solve it on smaller trees and put the answers together. That's what recursion is, right? Now, we don't know if any of these vertices is in the independent set. Okay? But we can pick it and then decide whether we want to keep it or not. So let's say we pick a node. So we pick a node and say, let's consider this node here. Either this node is in the independent set, the best one, or it's not. If it were in the independent set, what do we know the independent set will look like? Well, if this node is in the independent set, none of its neighbors can be in the independent set. So if this node is in the independent set, we can delete all its neighbors, right? And what do we end up with? We end up with these 3 pieces here. Well, these are all actually 5 separate pieces. What's the independent set of a collection of disjoint graphs? It's merely the union of the independent sets on each of the graphs. That's actually easy. If I have a graph here and I have a graph here, there are no connections between them. Then the independent set for this collection is the best independent set here, the union with the best independent set here. There's no interaction. You can do what you want. It's an easy recursion. So what we can say is that if you pick V, so pick any V, right? And then compute the MIS on the graph G minus, this is set minus, V and all its neighbors. So NV is equal to V and all its neighbors. Right? But suppose V was not in the tree, then well, it's just not in the set. You have to look at everything else to figure out where the set and what the independent set is going to be. So the other case, you just remove V, right? One of these two is going to give you the correct answer, right? Because either the optimal independent set contains V or it doesn't contain V. If it contains V, then it must look like this. If it doesn't contain V, it must look like this. Inductively, if I have solved, if I have a method that works correctly on all graphs of size n minus 1 or less, then by the induction hypothesis we'll work on this. So I have a recursive formulation of computing on the independent set. So I've described a subproblem. I've expressed this in terms of the subproblem. So this will be, and then so union. Right. So there will be the MIS of that, take a union or do. Okay, so the first thing we have to do is formulate the recursive problem. We've done that. The second thing we have to do is show that it actually, by induction, gives the correct answer. We just argued that. And then we have to unroll it. How many subproblems do you have? Well, the subproblems here are basically the original set of vertices minus any subset. One other way of saying this is that the set of subproblems are all possible subsets of the graph. But how many subsets of the graph are there? If you have a set of n vertices, how many subsets can you have? You can have 2 to the n subsets. So you could make your table of size 2 to the n, fill it out and solve this problem. Okay? But that won't work very well because there are 2 to the n of them. We want an efficient algorithm. If you wanted to spend 2 to the n time, you don't have to do anything clever. You just brute force it. So the fact that we have given ourselves a recursive formulation of the problem has not got us, via unrolling, to an actually efficient solution. We don't have a dynamic program yet. All we have is a recursion. We're like the Fibonacci recursion, but we haven't figured out something interesting about it to allow us to reduce the number of subproblems to a small size. Because that's the essence of dynamic programming. But here's where it starts getting interesting. And here's where you have to exploit more structure. This is not an arbitrary graph, it's a tree. Okay? And this procedure works with any node we start with. It doesn't matter where you start. Okay? So suppose we do the following. We take our tree again, which has been drawn up like this. And I said a tree was undirected, right? I lied. Let's pick our vertex up front and call it a root, just for fun. And because we're calling it a root, let's imagine all the edges sort of in our minds going outwards from it. So this goes out to this goes out to this. These are now my subroots. They go out there, they go out there, they go out there, they go out there, they go out there. We will never have a problem of a cycle because trees don't have cycles. Every node will have a single parent. And you'll never have a convoluted. How does this help us? This helps us now because we can now, when we do the recursion, we can say, oh look, we took V, we removed it, we have these subtrees of the graph. These are in fact smaller subproblems. So our problems are not just, I mean, okay, even the previous case problems were getting smaller, but there was no structure to them. We were looking at all possible subsets. Here there appears to be some kind of subtree structure. And the key step here is we can identify a subproblem with a small label. In other words, we can describe a subproblem in this rooted tree merely by saying, what is the root of your tree? If I have this root of the tree here, this is the whole problem and V is my root. If I decide not to pick V, I delete it. I now have one subproblem starting here. I have one subproblem starting here. This is again a rooted tree, described by that node as root. In other words, every subproblem has a label which is the root of the subproblem, of the subtree associated with that subproblem. And why is this label small? How many roots can I have? There are only n roots in a tree. There are only n vertices in a tree. So I have gone from a situation where in my recursion I had all possible subsets of the graph to a situation where by organizing my tree from top to bottom, by fixing a root and dropping everything like one node and everything falls down below it, I now can associate an entire subset with a single vertex label. So the actual number of subsets I need to worry about gone from 2 to the n down to n. Okay. Yes?
So maybe we can exploit that weakness because it's directed?
We can exploit that. We can create this fake notion of a direction and everything just goes down to leaves. There's a notion of going down to the leaves. In a general graph, there's no down, there's only around and around and around. Because there's no cycles here, you can exploit this idea that things, once they go away, will never come back. And so a direction is one way of saying that. So now we can say that the subproblem, so we want to find MIS of G, we express this in terms of MIS of V, which is find the MIS of subtree rooted at V. Okay? Subtree rooted at V. This implies a direction. So what I do is I start off by saying pick any vertex V, root the tree at V, which means make V the root and put all the things going down. So now we can say MIS of G is equal to MIS of V, because nothing has changed yet. The rooting has not changed the fact that we're looking for an MIS. We just said, okay, the MIS of the tree rooted at V, okay. But now I can express this problem recursively. Let's say V has children U1 up to UK, right? So then MISV, just like before, can be expressed as the max of two parts. One is where we don't pick V, right? So it's basically sum of MIS UI, or union, right? Because now I just take the subproblems individually and take the union. Or it's the union of, when I say max, I mean size of the set. I'm being a bit sloppy here. So, union of, let's see, MIS. Okay, so what's the best way of saying this? Union MIS WI I equal to 1 to R, where you think of WI as, let me draw this tree again. It looks like V, U1 up to UK, and then they have W1, W2, all the way up to WR. So now you've removed, not only have you removed V, you've removed all its children as well, right? So this is the don't pick V case, and this is the pick V case. Right? And now I actually have a formulation which is recursive and only has n subproblems. Now in the matrix version of this, if we have a matrix problem, we'd be done this one. We draw out the matrix, we look at the updates, and we get the flow of information. Of course, in a tree, you don't have that. If you look at this, where's the flow of information going? Right? Well, it's ending at the top. It's starting at the leaves of the tree. Again, a notion that makes sense only for trees. Right? Because every time you start the root, you go down, you go down, you go down, you go down, you express it recursively. So the base case for this bottom-up unrolling is the leaves of the tree. Right? So now my dynamic program, instead of going in a matrix or sweeping across the matrix and going across an array, is basically going bottom-up. So I have my tree, right? And my information flow goes from here. So when you unroll your dynamic program, you're going to build a tree, do the routing, and then start the leaves, and then build up some problems. And this works for any tree and for many, many hard problems, that you can formulate them as a dynamic program on that tree structure. Where you either pick the root or don't pick the root, in cases where you're picking some subset. So this is an example of where you're applying all the concepts of dynamic programming, but in a scenario where you don't have your typical arrays or matrices. So that's why I wanted to show this to you. That the concept is what's important here, the representation. And the same ideas apply. Find the optimal substructure, make sure your subproblems are few in number, understand the flow of information as you unroll, and then use it to build it up. Okay, questions? Okay, I will see you all Thursday. As an assignment to you,